afternoon, all of you. So, myself, Dr. Anjana Dokra from National Physical Laboratory, New Delhi, and if just to introduce NPL, NPL is the NMI of India, National Meteorology Institute. Basically, the institute which maintains the standards of the country. So, this is the basic introduction to NPL, and I'm sure you might be aware of that, because the chapter on NPL, I mean, there is small paragraph in class 11th or 12th about the measurement things where the name of NPL is being mentioned. So coming to my topic, what I am going to present today, the topic is impact on ferromagnetism with variation in BaRuO3 layer thickness in BaRuO3 LaNiO3 superlattice. So basically we are making these superlattice on different substrate. So I am going to discuss how we are going to induce the ferromagnetism in these kind of materials. So this work is basically the PhD work she is doing, I mean it's presently ongoing, it's kind of 1 or 1.5 years she is working, Anu, and then we have few people who are working on XRD and AFM, Gitanjali, Sandeep from NPL, and Dr. Satpathy from SINP Kolkata. He has done the cross-sectional TEM for us, and from IIT Roorkee, Professor Vivek Malik and his, one of the staff, Charan Singh, is also involved in this work. So, starting with the introduction, so why we want to induce the ferromagnetism in such kind of layer structures. Basically, when I am talking about these layer structures, they are the constituents, if we talk, they are not the ferromagnetic layers, okay, they are the paramagnetic layer which I will be talking about. So, why we are interested to create ferromagnetism at the interface of the paramagnetic layers, okay. So, heterointerfaces, if we all are aware, if we talk about transition metal oxides, AbO3 type, they are usually exhibiting exotic properties, very much different when they are moving from bulk to thin films, or you can say the nanostructures. So, why? Because of the existence of coupled degree of freedoms, okay, and which provides the promising platform for the exploration of emergent quantum states. So, that is one of the reasons which we want to explore. And second is, along the this, if you talk about the interfaces, so charge reconstruction and interlayer exchange interactions can take place. So, which can basically introduce a lot of unique properties in these kind of materials, okay. And a lot of work, if you see in the literature, is existing when the layers are ferromagnetic or antiferromagnetic layer, the combination of ferromagnetic, antiferromagnetic with the paramagnetic layers, they are existing. But the issue with such kind of superlattices or the interfaces is that they induce strong pinning effect at the interfacial state, okay, magnetic states. So, what is happening? So, it is you cannot manipulate the magnetic moment. So, if you cannot manipulate the magnetic moment, then there is the restriction for the applications. So, if you want to introduce more applications towards the basically the, you can say, the quantum states, then you have to avoid such kind of pinning effects. So, how we can avoid? Basically, we can take something, the layers or the superlattice of paramagnetic kind of layer structures, okay. So if interfacial ferromagnetic phase can be generated in the heterostructure consisting of two non-magnetic constituents, the magnetic moment would become more tunable. So, that is the major purpose of this work, okay. So coming to the BaRuO structure, if you see there are several phases of BaRuO3, as in the, if you take the bulk form also or in the thin films as well. So, it has 9R, 4H, 6H and 3C. These are the different phases, and you can see the susceptibility. Okay. So, if you go to the 3C phase, then only you will observe the ferromagnetism or magnetic character you can observe in these kind of structures. However, when you move to 9R, then the magnetic moment will reduce. So, how it is being generated? Basically, in bulk, what people have done, they have created the pressure, and the pressure of the range of 18 gigapascal, and the temperature was about 1000 degrees Celsius. So, this kind of particular parameter when they have done, then the structure has moved from 9R to 3C. Okay. So, now our interest is whether we are able to create such kind of pressure with some other kind of technique and get the 3C phase in these kind of BaReO3 structures. So, one of the paper which we found, it is from 2021, Lee et al. In Advanced Electronic Materials. They have shown that they could stabilize the 3C structure of BaReO3 thin films, and very good. You can see this cubic phase, I am sorry, this one. So, cube on cube you can see. So, 3C structure is confirmed, and they could also show the transition around I think 48 degree Celsius, and they could also show the ferromagnetism in the this BaReO thin films. So, from since we are making this BaReO3 and LaNiO3 interfaces or the superlattice, so we would like to understand what exactly these materials are and how they behave. So, BaReO3, already I said that they are existing in several phases, 9R, 3C, etc. And also if you are able to create some epitaxial strain, then also you can stabilize the 3C phase in these kind of phases, I mean the structures of BaReO3. And also if you look for the metallic transport, which is again this paper Lee et al. Has mentioned in Advanced Electronic Materials, they could get the 3C phase and they could show the non-Fermi liquid behavior near the magnetic transition. Okay. And coming to the LNO, which is LaNiO3, so it also modifies with the strains. Okay. So, this is the paper which was published in 2017, and they could also show a metal insulated transition when the film they have reached to very ultra thin structures. So, then this kind of transition they could observe. Okay. And in bulk, as I mentioned, they both are paramagnetic structures. So, taking these entities, so we have seen like what kind of, if in literature whether such kind of studies are available or not, we did not find a combination of this particular combination, but we have seen there are certain paper where we have SRRuO3 with LaNiO3 and CaReO3 with LaNiO3. So, what we have observed the basic difference, because here we have different phases, but these kind of things are not existing here. They are very much orthorhombic or tetragonal phases, very stable structures, and because of the some strain, I mean they could show the spin orbit coupling, and for CaReO3 it is again they could show, but it is weaker strain or orbit coupling. And very much like if you talk about magnetic ground state, ferromagnetic for SRRuO3, it is very much ferromagnetic, at the Tc was 150 Kelvin, and CaReO3 was paramagnetic. And for BaReO3, as I said, it is paramagnetic, but strain can induce the weak ferromagnetism. Okay. So, seeing these kind of like also coming to the interfacial magnetism, which is our the topic of the presentation. So, strong ferromagnetic coupling with LaNiO3 people have observed is SRRuO3, and something people have also observed with the CaReO3. So, looking at these kind of literature, we have chosen these BaReO3 of the like similar perovskite family to look into whether we are able to induce the interfacial magnetism in these structures or not. Okay. So, when we talk about CaRuO3 LNO superlattices, so this is one of the paper in ACS Nano 2024 by Zhang et al., where they have shown that when they change the layer thickness, like this is C2L2 and you have C10L6, so you can see the conductivity. It is very much semiconducting, kind of like metallic, but kind of semiconducting, it goes to the semiconducting nature. However, when they move to the anomalous Hall effect measurement, you can see this Hall bar they have generated. So, they could see the good hysteresis at various temperatures. Okay. So, the size of this hysteresis changes with the temperature, and all these kind of representing the same thing. Okay. So, they basically you can see how we can correlate these kind of hysteresis, because they are also showing a kind of induced ferromagnetism in these structures. So, they have correlated these structures to the change in the hybridization. Hybridization of what? Ru, because ruthenium is there. So, basically the T2G level is going, basically there is a, you can say, the charge transfer from ruthenium to the nickel. Okay. Because of this charge transfer, these kind of, you can also talk about the valence state is changing for the nickel. That is why the magnetism is being observed, and they have done the XLD measurement. From XLD measurement, if you see this nickel LH, so here you see this is the negative. Okay. So, IAB minus IC, basically you see the negative from the XLD. However, when you see this oxygen KH, so it is positive. So, when you are moving from this nickel edge to the oxygen edge, so this is basically representing that the induced ferromagnetism in this material. Okay. So, basically to say this is the signature of the ferromagnetism in these kind of materials. So, second feature which people have observed in similar structures, what they have observed is the super exchange mechanism. Okay. And also you can say the step in the hysteresis, and they have correlated these steps to the different corrosive field of ruthenium and the nickel. Okay. Okay. So, coming to our work, so what we are aiming to induce interfacial ferromagnetism in these kind of superlattices, and before that we would like to stabilize our cubic phase of BaRuO3. On the at present our focus is on STO substrate, and then later on BRO, LNO, STO superlattices with varying the different thickness of the layers we would like to basically optimize, and then whether we are able to induce the ferromagnetism in these structures or not. So, how we believe that we can stabilize the structure, cubic structure or not. So, because our method to prepare these films or the superlattices is the pulse laser deposition. So, pulse laser deposition, when we are growing in the thin film form, so some kind of chemical pressure also we are creating inside the material. So, because of that chemical pressure, or you can say because of the confinement of the sizes also, there are the chances that we are creating some kind of pressure inside the material. So, because of this creation of the pressures, different pressure what we were talking in the bulk, so we may induce the cubic phase in these structures. Okay. And second thing is, when we are growing this these kind of superlattices on let us say STO substrate or any other substrate, then there are chances that we could create some kind of epitaxial strain in these films. So, because of the strain also we may look for the ferromagnetism in these materials. And so, basically we will be strain engineering in these materials. And when we are talking about strain, so there is one paper, very good paper by this group in advanced material from 2011. So where they have talked about, like when you have compressive strain, then the hybridization is basically because of the TZ2, and when there is a tensile strain, then you have the hybridization which is correlated to the dx square y square. So when your hybridization is changing, then your strain is basically coming into the picture. Okay. So how we will be controlling this orbital hybridization? By controlling the substrate selection and film thickness, and third will be the various deposition parameter which are there in our hand. So these are the sample details what we have, like these are this kind of superlattice we will be making. STO is our substrate, and then BRO LNO, and top is our BRO layer. Okay. So as I mentioned that we are growing our films with the pulse laser deposition, where the energy density of our laser what we have used is 1.2 joule per centimeter square, and frequency at the rate of 5 hertz, and the pressure what we have maintained while deposition was low -3 millibar, and temperature we have fixed to the 750 degrees Celsius. So we have not modified these parameters, we have just played with the thickness of our layers. Okay. So these are the lot of samples you can see which we have made from, like you can see this BRO thickness. Here we are, if you notice, here the BRO thickness we are keeping 4 nanometers stable, and we are changing the thickness of the LNO. Okay. And for certain other films we have also changed the BRO thickness to just see I mean the layer thickness effect. So coming to the results, so this is the target we have prepared for BRO3 and other LA NIO3, both of them were by the solid state technique, which were very much good, I mean stable structures which we could get. And in this right side image, if you see, this is the thin film which we have grown with the PLD. Okay. So these two data point which you are seeing, one is at 10 raised to -3 millibar and 10 raised to -2 millibar. The purpose of showing this particular graph is that both the pressures we are able to get the epitaxial thin films for these BRO3. Okay, at 001 plane. And while going to this, here you see BRO6 and LNO5 in the high resolution XRD. This also shows that very good epitaxial nature films we have, we could fabricate. Okay. So I mean if you see, there is no other you can say neighboring peak because of the I mean it is very much matching with your substrate. The film is matching with the substrate, it is very coherent film, that is why you are seeing this kind of structure. Now the similar results we could see from the XRR, the superlattice structure. I mean the fitting, I mean there is little, I mean still we are into this phase of doing, I mean probably we can improve it, but the layer structure of superlattice could confirm from this XRR measurements. Then the quality of the superlattice, whether they are really abrupt or not, that we need to look into that data. So what we have done, the cross sectional TEM which Dr. Satpathy has done for us, and if you see this layer structure, very sharp abrupt layer we could see for these superlattice of BRO LNO on the STO, and the thickness what we have taken, while because we have adjusted our thickness on the basis of the number of shots which we were putting. Okay. So we were taking like 5 and 6 nanometer for BRO and LNO, and from cross sectional TEM also we could find that they were matching with the thickness what we have already deposited. Okay. And this pattern FTT pattern also shows the good I mean the good structure for these kind of sublayers. But here we are seeing that these kind of layers are very much abrupt. For strontium, nickel, not for strontium, we are okay, I mean is fine. But for if you see for nickel and ruthenium, some kind of like for the whole layer of, you can say, in the thickness, you can see the for whole films this Ru you are able to see in the cross sectional term, and same with the nickel. So here I don't know, we were not expecting this because of this abrupt what we were seeing here, but we are thinking that probably because we have I mean every layer by BRO, LNO, so probably because the whole system goes like this, that is why we are saying, but I am not sure about this, but we are not expecting this kind of result. So coming to the AFM data, so here also the uniformity of I mean very uniform AFM data we could see, but with the thickness this roughness has gone, I mean the roughness increases with the thickness. This is the very less roughness here we could see, I think 0.7 nanometer or 0.67 nanometer for the thickness of 36 or 38 nanometer. So just to make sure that we are not getting our results from STO, I mean any ferromagnetism in STO or BRO layer, so very good diamagnetic behavior we could see. So we just to bring the confidence that these layers are very much diamagnetic. Now coming to the magnetic measurements, so this particular data is for where BRO is 4 nanometer, LNO is 5 nanometer. Okay. So if you see this magnetization is done at various temperature 4 Kelvin to 300 Kelvin, and hysteresis for all the temperature we could receive for these superlattices. So we are we are able to induce this ferromagnetism in these kind of layers, and the hysteresis if you see, like I mean the corrosive field is fine, but for the 300 Kelvin we are seeing this crossover at 300 Kelvin. So I mean we are still understanding why we are I mean we cannot correlate to super exchange or anything else, but what reason behind this crossover we are still seeing into it. Okay. But rest of the temperature they are very much I mean as we were expecting, so we are getting those kind of results. Now when we are see this particular layer what we have said, yeah, BRO 4 nanometer, LNO 5 nanometer. However, when we change the thickness, BRO is 4 nanometer and LNO when we have changed, this is the 3 nanometer and this is the 2 nanometer. The drastic change in the this hysteresis loop you could observe. So I mean for 3 nanometer still there is a mild hysteresis we could see, but it's completely paramagnetic for the 2 nanometer, which we have generalized that this is the optimized thickness. After that only you will observe some kind of induced ferromagnetism in these kind of superlattices. Okay. Then moving to this 2 nanometer, then we have reduced the thickness of BRO layer 2 nanometer and LNO 5 nanometer we have fixed here. So a very anomalous nature of the hysteresis which we have observed, if you see for 300 Kelvin the hysteresis and the saturation has gone up, and the 4 Kelvin it is quite low. So this is very much anomalous than what we generally were expecting, and which we have observed for the where we have the BRO layer thickness was 4 nanometer. Okay. And also there is a step kind of things are also observed in this corrosive field, where of course we can correlate to the corrosive field of ruthenium and nickel. So this is easy to understand. However, that crossover which we were observing for 300 Kelvin for the earlier superlattice, here we have observed for the 100 Kelvin. Okay. So some kind of like there is a possibility that it is a we are able to induce ferromagnetism, and there are the ferromagnetic domains. However, there are certain signature of diamagnetic entities as well. Okay, so maybe because of that entities we are getting such kind of signature in our hysteresis loops. So this is the, like what I was telling that, I mean this, the corrosive, the step kind of behavior in hysteresis people have observed in SRRuO3 NIO, and where they have correlated to this pinned, they have discussed that the layer of SRO is pinned between the NIO layers. So this pinning effect is happening in these kind of system, that is why this kind of step kind of behavior is observed in the hysteresis. Okay, I am just finishing. So this two more slides I would like to just share, because you can, when I was telling that we can tune the ferromagnetism in these kind of system, why I said, because if you see this slide, I told that in all the layers we have BRO at the top layer. Okay, when we are going this superlattices, BRO is the top layer. And then we have tried another combination where LNO, all the layer thickness was same, but LNO top, we have made the LNO as the top layer. So if you see there is a huge difference in the hysteresis itself. I mean there is kind of, you can say there is not even saturation can be observed for BRO when BRO is top layer. However, very good saturation is observed and for all the temperatures. Okay. So if I magnify these images, so if you see for this LNO top layer, here also some kind of steps are being observed in the hysteresis, and this area of the hysteresis increases. However, for BRO top layer, you have, this non-saturation, more kind of, you can say ferrimagnetism kind of thing we can talk about, or we can discuss about this, and the signature of the hysteresis steps is also changing with the change in the BRO top layer. So these clearly signifies that if we want to control this ferromagnetism in these systems, so we can really tune as per our choice. How we can induce the ferromagnetism. So this is the okay, one more slide which I would like to share. These all data is with the STO substrate. However, when we change the substrate, to LSAT, here also we have made this BRO top layer and LNO top layer. So you can see the hysteresis for BRO for LSAT. So we could see the hysteresis which is not saturating, but still we are able to see the hysteresis. But here the loop area has reduced and it is at very low magnetic field. Okay. So still these results, the student is working and we are under the, just understanding these, analyzing these results, why these things are happening. And so this is what from our side. Okay. Yeah. So with this I can conclude that interfacial ferromagnetism phase induced in the superlattice consists of two paramagnetic oxide, which is BaRu3 and LaNiO3. Then the major reason which I was explaining in the first two slides, it can be charge transfer between ruthenium and the nickel, or you can say there is a which can trigger the super exchange phenomenon between ruthenium, oxygen, nickel, and which can give rise to the ferromagnetic phase. So tailoring of ferromagnetism is possible with thickness of the layers. With this I thank you for your time and for listening, and our funding from CEFIFRA, the Indo-French project, and the CSIR. Thank you.
Thank you. So now open for questions. 3 questions. Okay. So if no questions, let's thank Dr. Dogra.
Okay, thank you.
That was a nice presentation. So
thank you. Thank you.